Good afternoon, everyone. I'm very honored today to introduce today's IAS distinguished lecturer to give the seminar. And his name is Professor John Charles Crittenden. And you can, nowadays, you can Google to find who he is, right? So he's a very famous environmentalist and working on quite a wide range of subjects, and from nanotechnology to meso to ordinary and giga. So all the technologies that involving the sustainability study. And in fact, this time before he came here, he gave me two titles to choose. One is on gigatechnology, another is on nanotechnology. And I choose the Gigatechnology. I thought we have heard so many people talking about nano. And so Gigatechnology probably will be, make this kind of series of talk more complete. And so he is now Hightower endowed professor at Georgia Tech, and also serve as the director of Institute for the Sustainable Study. And he's elected member of National Academy of Engineering, US, and also that of China. And so we just know that both are quite prestigious and difficult to get in. And you're not going to talk about how you get that in, but we congratulate you on that and look forward to your talk.
Okay.
And please join me. Welcome, Professor John Crittenden.
Well, thank you so much for inviting me and giving me the opportunity to talk about one of my favorite subjects, generally speaking under the category of sustainability. So I thought I'd say a few words about Georgia Tech, because maybe some of you don't know about Georgia Tech. And I know China's rankings are always very prominent on their mind, so I want to go over that briefly as well. So our annual budget is about $1.5 billion. We're located in Atlanta. The campus occupies about 1.6 square kilometers. We're the largest engineering school in the United States. I know this is small by China standards, but anyway, we have about 13,000 students. Actually, it's about 15,000 now. These numbers are a little bit dated. Research expenditures approaching now $750 million. And then the rankings, as I promised. So in School of Civil Environmental Engineering, Georgia Tech is ranked number 2 ahead of Berkeley and MIT. And then for the graduate program, we're just behind Stanford and Berkeley, again, ahead of MIT. And then Shanghai Jiaotong ranked Georgia Tech as 6th among the world's top universities in engineering, technology, and computing. So, and if you don't believe those kinds of rankings, you can just look at citations. So this is total number of citations from 1999 to 2009. We ranked number 6 ahead of the Chinese Academy of Sciences, just behind Michigan, Stanford, UC Berkeley, and Illinois. Okay, so I also have quite a few collaborations with Chinese scholars who come to our school and work with me on a variety of subjects in water treatment as well as sustainability. I don't have time to tell you about all the folks that have visited us, but it's now a total of 72. And they come from all over China. Just give you this quick graphic here. And then some of the collaborative projects are shown here. Membrane technology, water splitting for hydrogen production, advanced oxidation. And we're also doing some work on eco-industrial parks in China looking at stainless steel, or the steel industry, I mean. Okay, now to my subject. So this is an outline of what I'm going to talk about today. And So first, I think I'll talk about, what is sustainability in the Gigaton problem. Before I really talk about that in depth, I want to give you an overview of how important urban infrastructure is. So first of all, the current world population is about 7.4 billion. The projected population by 2030 will be somewhere around a little bit over 8 billion people. The Earth is only 29% of the Earth is covered by land, and urban areas only occupy about 2% of that. But cities are responsible for 50% of the greenhouse gas emissions, 60% of the population, 70% of the global energy use, and 80% of the global GDP. So cities are very important. And we're going to see, as we move toward the future, that the numbers are going to increase in cities in terms of urban dwellers. A point that I'd like to make without digging too deeply into the words that are written on this slide is there's two, I think, important things that we need to focus on when it comes to designing urban infrastructure. And one is a systems level view. And I'm going to emphasize that as we move forward. And then another is managing complexity. And so that brings up some things in your mind. What is complexity? I'm going to talk to you a little bit more about what I mean by complexity in a moment. But so those two areas, I think the greatest accomplishments when it comes to sustainability will be managing complexity and a systems view. So first thing is we have to understand this process where we extract resources to create desirable goods, and then these often have pollution and waste associated with it. And then these goods, even if they're durable, eventually end up as waste. And one thing I'll put this slide up for is to emphasize the fact that we have to also manage the demand side of sustainability. We can't engineer ourselves out of this problem, because if we demand too much of this, we're going to generate too much of this, such that the Earth cannot assimilate that. So we can't just, technology alone is not the answer. We also have to think about reducing the demand for these things and thinking of alternatives. So let's talk about the problem a little bit. Call this the great acceleration of increasing human activities. And I think probably you can't read all the X and Y scales, but each one of these is time starting at 1750 going to the year 2000. And then the vertical scale, I'll tell you. So 1750, we had 500 million people. Now we have 7.4 billion. Actually, the GDP now is about $78 trillion. Fertilizer consumption, somewhere around 350 million tons. Water use is very, very high, on the order of 5,000 cubic kilometers per year. Damming of rivers, 28,000. Paper consumption, 250 million tons. McDonald's restaurants, 35,000. Motor vehicles, we have about 1 billion, and so on. So what happens when we have this tremendous increase in activities through these human activities? Well, they have impacts on the environment. Again, the same scale going from 1750 to 2000. We see the CO2 levels from about 265. Now today it's 400 and a little bit. N2O concentration rising from about 270 parts per billion to 310 parts per billion. This gas is about 300 times more potent as a radiative trapping gas than CO2. Methane has increased dramatically, 850 to almost 2,000 parts per billion. The columnar ozone, this is the ozone in the stratosphere that filters out the UV rays. We've lost about 70% of that. We have a greater incidence of floods. How about this? We've exploited, in terms of the fisheries of the ocean, about 80%. Imagine that. The ocean is so huge. How could we possibly exploit 80% of the fish in the ocean? Some talk about the end of wild fish. It's coming. And biodiversity loss. Here's another one. Percent of 1700 value. How much has been lost in the tropical rainforest? About 35%. So these are the impacts that we've had. Clearly, this is not sustainable. Okay, so now what I want to do is talk a little bit more in detail what is sustainability in the Gigaton problem. I'd like to start out with saying something very simple and then translating that into numbers that engineers can relate to. We need to recreate the anthroposphere. That's a place that we live, to exist within the means of nature. And that has two basic criteria. We have to use renewable resources. That's one. And the second is we can't generate more waste than nature can assimilate without overwhelming natural cycles. So that's going to require us to look at the interactions between the natural, engineered, social, and economic systems in a whole new way. And maybe I can convince you that we've begun to make some steps towards that. So let's first take on the first premise of sustainability. That is generating waste that nature can assimilate, not generating too much waste so that nature can assimilate without overwhelming cycles. So to really take on this problem, we would need to look at a variety of things, including the fate of toxic organic or toxic compounds, nitrogen, phosphorus, water, carbon, and more and more and more. I could spend an hour just talking about the report card, that is, how well are we doing with respect to living within the means or not providing overwhelming natural cycles. So I won't be able to look at all of those, but let's just take a couple on. First, let's talk about the nitrogen cycle. The nitrogen cycle we've had a tremendous impact on. Now, what we do is we take nitrogen out of the atmosphere and we create ammonia, and then we use that for fertilizer. That's probably one of the largest geoengineering experiments ever conducted. And basically, the protein in your body contains nitrogen. 2/3 of that nitrogen came from fixing nitrogen from the atmosphere and making ammonia. Well, the big thing about this is about 1.2% of the global total energy consumption is related to us interfering with the nitrogen cycle. So we take the nitrogen out of the atmosphere, we make fertilizer, then we consume food, and then that nitrogen ends up in wastewater, and then we use energy to remove that as well. So it's quite a challenge. It makes sense to try and recover some of those nutrients. The phosphorus cycle, it's not like nitrogen. There's a limited amount of phosphorus out there, and the global reserve is thought to only last about 125 years. So in the long term, we've got to really do something about this. So you can see that we're sort of failing on these two in terms of interfering with the natural cycles. Now, carbon I want to spend a little more time on because we all heard lots about carbon. There's basically three choices out there: the 2-degree scenario, 4-degree scenario, and a 6-degree scenario. We're talking Celsius. To achieve those, we have to start, well, currently we're about 10 gigatons of carbon, and the current trajectory is going to take us up to about 16 gigatons of carbon. That's a 6-degree scenario. If we want to stay at the 4-degree scenario, we can continue to emit about 10, 11 gigatons of carbon. And if we really want to go down to the 2-degree scenario, we've got to start this trajectory that's going to scare you to zero by 2100. I'll show that next slide, but that's a big change, let alone the 1.5 degrees Celsius that they've agreed to in Paris, which is, I'll say something about. So this is from the IPCC, and here you can see that there's their projection to get to the 2-degree scenario. Basically, that last projection was only to about 2050, but to stay there, we basically have to stop at around 2100, no CO2 discharge. That's a huge challenge. And just in case you don't believe me when I say I think the 1.5 degree scenario can't work, NOAA already says we're at 1 degree, so we only got a half a degree to go. So, all right. So how can we go about this? And this is a famous McKinsey chart, which shows the abatement cost. The abatement cost in euros per ton of CO2 equivalent. Now, the previous graph, I was using CO2 as CO2. But if I want to express it as just carbon, it's 12 over 44, which is the molecular weight of CO2. And so the number over here isn't 38. To keep it equivalent, it would be 10.3 gigatons as carbon. Anyway, starting on the left, we'll see some negative numbers. That means that you actually get a payback for this. So over here you can see switching from incandescent bulbs to LEDs. You know, you actually you get a benefit right away. Or cropland management, electricity from landfill gas, and so on. About right in here is when we see the transition where it actually costs you some dollars to abate that CO2. We can see here low penetration of wind, solar, concentrated solar plants, solar PV, and so on and so forth. So there's a way to get there. It's going to take some energy to do it and a significant amount of dollars, but it's not something that's going to overwhelm our economy. In fact, I look at it a different way. Our economy is going to be different. We're going to have different kinds of jobs. It's not like we're going to destroy the economy. We're going to create new jobs in new fields. Okay, so I have to say something about farming. Let's just say, so if we look at, really talk about unsustainable farming, did you know that 30% of the ice-free land on Earth is used to raise feed for animals? 30%. That's a huge number. And probably only 2 billion people out of the 7.4 billion eat meat like we do in a Western society. And I know Middle Kingdom, I guess I'll have to call you guys the Middle Kingdom. So that's just not sustainable in the long term. And if you look at the resources for chickens and pork and cattle, the amount of water is unbelievable in the feed. So for a chicken to get 1 kilogram of chicken, we got to feed them 2.5 kilograms of feed, about 4 cubic meters of water. For pigs, 5 kilograms of feed, 5.5 cubic meters of water, and for cattle, 10 kilograms of feed and 16.7 cubic meters of water. So that 16-ounce steak you had, just that water in that steak could be 2,200 gallons. It's a lot of water. In fact, each and every one of you needs 4 cubic meters of water every day. So if you're thinking about, oh, I'll take a shorter shower or not eat meat, that's probably the way to go. Well, I don't want to try to make you feel guilty, but I think there's solutions out there that we should think about. And that is to create green food. There's some tech startups that are trying to make green food, and the opportunity looks like it's out there. So the idea is that we want to create animal-based products, plant-based products that are as satisfying as animal-based products with a much lower environmental impact. They mimic the taste of animal-derived foods, only we use plants, and we use a lot less energy and water and other inputs. But the hope is that we have 400,000 species of plants, and each species has tens of thousands of proteins. So it seems like it could be possible. I'm not near my local grocery store because I could have brought some of the stuff in for you to taste. But here's some examples. There's a plant-based chicken strips called Beyond Meat. Tastes just like chicken. I've had it. It's pretty good. Eggless mayonnaise by Hampton Creek. That's pretty good. And then there's another group that started this Impossible Foods. They wanted to make beef patties that taste and have the texture of beef. Unfortunately, at the initial run, they said that the beef patties tasted like rancid polenta, so they have a little ways to go. Another one that has been developed, it's a drink you take 3 times a day. It's made out of soybeans and lentils, and it's a complete substitute for food. In fact, the CEO of the company who made this has converted his kitchen into a library. So, and then occasionally, he calls it occasionally, goes out and eats dinner outside, and he calls that recreational eating. I'm not sure I'm ready for that, but anyway. Okay, second premise of sustainability, using renewable resources. So first I'll look at those materials in commerce, not including food and fuels, because that's a big fraction, and then I'll look at all materials. So first we'll just start with materials and commerce. So we can see this trend line here. This is dependence on non-renewable materials starting from 0 to 100%. And then we have a timeline ranging here starting at 100,000 BC, 10,000, 1,000 BC, and then on up. I'll talk about this as we go. But here in Neolithic times, basically all we had is bone and stone. That was 100% renewable materials. And then as we move further, wrought iron and bronze, we began to see an uptick. And then eventually the start of the Industrial Revolution, now we're having somewhere around 60% of the materials we use in the economy as non-renewable. And as we move up, we can see concrete replaces wood in large structures, aluminum displaces wood in lightweight design. Then we have in around 1940, metals become the dominant materials of engineering. And then we have oil-based polymers in the late middle of the century. And then we have silicon-based materials for information, communication, and technology. And at this point, we have 96% non-renewables. So yeah, since 1800, we can do it for 200 years, but we can't do it for 1,000. Or can we do that for 10,000? It's impossible. So we're going to have to do something about this. Okay, so those materials, only 4% is renewable. Now again, I'm excluding food and fuels. So let's have a little graph, take a look at what the trends are. So we'll have here metals and polymers, ceramics and fibers and hybrids. Here you can see this is annual world production in tons per year. Here we have oil and coal right around 10 gigatons or billion tons. Steel just below a gigaton, all the way down the line here to gold. And then for polymers, polyethylene, polyvinyl chloride, polypropylene, PET. And then ceramics, cement is very high. Asphalt, glass, and brick. And then wood, I guess we could consider that renewable. Natural fibers, perhaps, and man-made fibers and carbon fibers. So that's what the lay of the land looks like. And you notice a little block next to some of these materials, like steel, 538 gigawatts. That's how much energy we need to produce the steel. Or concrete, 340 gigawatts. Or glass. You see those big buildings out there with a glass apron on it. Think about how much energy it went into to create that glass. It's a lot. Energy required for the top 7 materials is about 1.5 terawatts, or 10% of the amount of energy that we use in the world economy. Hence the gigaton problem. So this is what it looks like. Over here we have 7.4 billion people. Now when we add food and fuels into this, we have 78 billion or 78 gigatons of material that's used in the world economy. Only 28% is renewable. Energy use in terms of tons of oil equivalent, 13.4 gigatons or 18%. Carbon emissions from fossil fuels, 8.6 gigatons. Water use, 4,000 billion cubic meters, or about 43% of the available fresh water. And passenger cars, about 1 billion. So we have a gigaton problem, and I think I've explained it well enough. And first, in terms of renewables, and second, in terms of producing too much that overwhelms natural cycles, in the case of carbon, overwhelming the Earth's planet, the planetary system, such that we get global warming. And all this discussion up here is the following. We just can't afford to do this, and if we think about if we move towards 2050, maybe there'll be 9 billion people. The golden billion, like some of us sitting in this room, we're the ones who created this gigaton problem, and it already looks unbelievably large. But if we really want to design it for the future, multiply all this by 10. Does that scare anybody? Because from an egalitarian point of view, the rest of the people on this planet are going to want to have the same kind of lifestyle as we do. So this is my report card for the world economy, and our current GDP is about $71 trillion. I don't want to see doubling of the economy and any of these numbers going up. In fact, they've got to go down. So when you see these numbers like, oh, energy per dollar created, that's going down. But when you multiply it times the number of dollars being used, or dollars being created, they actually we use more energy than we did before. So that's not acceptable. As long as we use renewable energy, it's okay. Okay, so I have painted a picture here for you for two possible Earths. I don't know if you've gathered what I'm trying to tell you. So as we move forward, maybe we have complete segregation between the human and natural environment. Even larger scale geoengineering projects take over. We now live in our own microclimate bubbles. It's too hot out there. It's too polluted out there. We can't live out there, so we have to create this environment where we live. Maybe we have fusion energy, top-down governments to make it all viable. Engineered foods replaces conventional agriculture. Okay, that's one possible outcome. The other one would be to reintegrate human and natural environment. Really look at accelerated, drastic efforts to reduce emissions, restricted use of fossil fuels, policies in effect to mandate the use of renewable resources and energy, and bottom-up rebuild of our economic system, taking into consideration externalities, and then responsible agricultural practices to sustain the food system. Something to think about. Okay, so what I'd like to do now is talk about transforming the urban infrastructure and looking at the role of what I call infrastructure ecology. Okay, so let's get the lay of the land here. So by 2025, here's the challenges for China. 5 billion square meters of road will be paved. 170 mass transit systems will be built. 40 billion square meters of floor space will be built in 5 million buildings. And just for fun, we'll add another terawatt of energy. And you'll now understand why I called it a gigatechnology. Did you know that China used more cement in the last 3 years than the United States used in a century? Does that scare anybody? That's about, that's about 10 to the 14th moles. It's a big number. I'm going to skip over that one. But there's hope out there. It seems that in urban infrastructure, we're going to spend about $70 trillion on telecom, road, rail, water, and electricity infrastructure. Because we're going to double the urban infrastructure in the next 35 years. And just for the fun, I need to point out that it took 5,000 years to get to where we are right now. And the US will increase by 30 to 40%. So there's opportunity to do it right as we move forward. Unfortunately, I'm running kind of slow here, so I don't have a lot of time to explain the principles of infrastructure ecology, but they're here. I'll talk about this, managing inherent complexity, decentralized to increase response to diversity and modularity, maximize sustainability and resilience, take into consideration stakeholder preferences, maximize the creation of comfort and wealth, and a whole bunch of others, which I can't really get into, but we developed these principles, and we've got a paper published on this, which you're welcome to read. Okay, so now let's start talking about the system level thinking and how all this stuff begins to fit together. Many of you have probably heard of the water energy nexus. That is, water is required for energy production, and also energy is required for water production. So depending on what the energy source is, the amount of water that's required varies dramatically. So for example, hydropower requires about 18.27 gallons per kilowatt hour. The reason is you have a big reservoir and water evaporates, so you lose a lot of water. Nuclear, a little bit more than coal because it's a little hotter, and then some of the other numbers. And then over here we can see the numbers for kilowatt hours per million gallons. And we can see that if we have really high quality surface water, the number's lower than if we're trying to use desalination. We need water for transportation as well. This is a variety, this is gallons per vehicle mile traveled for a variety of technologies and vehicles. So for example, corn ethanol, this is the vehicle production, how much water is needed, and then that's how much is used for fuel. Switchgrass irrigation, that's the amount of water for the vehicle, and that's how much the total is for fuel consumption. So you can see that biofuels can have a very huge impact on the water demand. I know in China there's a program to policies for increasing the use of electric vehicles. This slide is meant to remind you of the fact that it takes water with the current energy production to create the electrical energy that then used in the cars, used by electric cars. And here you can see that 91 million gallons per day would be required if we had 100% penetration of electric vehicles. And that's almost equal to the domestic water consumption or evaporative loss. So that's not acceptable. All right, so let's continue this discussion about other technologies. There's a thing called low impact development, and even Xi Jinping talks about a sponge city as opposed to a city where water, it rains down and runs off. So what we did in the past is we basically scraped off the ecology, replaced it with hardscape. It rains, and we get surface water runoff, carries pollutants, causes flooding, causes erosion, and so on. So the whole idea with low impact development is to reduce stormwater runoff erosion and reduce surface water contamination. And I got a couple of plots here, pictures of ideas. One is a rain garden, which basically controls the water and lets it flow out slowly. Green roofs, rainwater harvest tank here. And then we can also have these green alleyways where we treat the water and it runs towards surface water. And these green alleyways are nice for pedestrian walkways, maybe bike paths and so on, and then porous pavements. Okay, so let's have a look at the water flows with LID and reclamation. So this is for a 2-story apartment in Atlanta. And all these numbers are gallons per capita per day. But basically, this shows you what you might need it for. So we have, in the case of rainwater harvesting, we use some of this for toilet and laundry and outdoor. And then we still need a centralized plant to make up the difference for potable water. That's 35, and that's for shower, hand wash, and dishwasher. And then that ends up as wastewater. And then if we do gray water reclamation, we can take the laundry and bath and some of these other dishwasher stuff, and we can take that and have an on-site wastewater reclamation system, and then that can be used for non-potable use. So now instead of having a lot more water here, we need less water to the system because we have one internal loop where we recycle it, and then downstream we have a much smaller wastewater plant. So we have a much higher concentrated wastewater than we would up here. And then the next thing, of course, is that we could just take, the rainwater and then use that as the water source and be totally off the grid. So, and that would be interesting because now we have a smaller wastewater treatment plant downstream and we have a more concentrated wastewater stream, which leads into this slide. So if we have LID technologies here, we get a more concentrated wastewater. This allows us to have a greater energy efficiency and removal of nutrients and energy from the wastewater. Maybe we don't call it wastewater anymore, we call it resource water. And then we can use those nutrients for urban farming, for example, and then recover some of those energy for the energy infrastructure, and then create all this green space over here, stormwater management, water recharge, and then we have a lot of social benefits as well, such as, I already mentioned, heat island mitigation, public health, because people now have a little opportunity for walking, urban gardens, and so on. All right, another systems view. I'm sure you might have enjoyed the Winter Olympics when it was held in Canada. And this shows the False Creek neighborhood energy utility in Vancouver. And they actually take the heat from the sewer. And this, the sewer heat supplies 70% of the annual heating demand and reduces greenhouse gas emissions by 50%. Okay, another energy option that I'd like to talk about is called decentralized energy production. And these are air-cooled microturbines, so there's no water used, because typically in a large electric power plant, we reject heat by evaporating water, so that causes energy-water nexus. So what we have is a furnace, basically, that creates electricity, and then The heat that comes off of this can be used to heat this building. It's about 2,000 square meter building. And so that heat can be used for heating and hot water. And then during the summertime, we can convert that heat into cooling using what's known as absorption chiller. And this will reduce the water demand by 50%, CO2 reduction, and NOx reduction, which produces PM 2.5. And so we thought this a little bit further. The conventional system is shown up here at top, where basically you have a building, you have electricity from the grid, then you have a furnace or boiler that supplies heat. And this electricity is used for cooling, heating, and hot water. But our proposed system now has many more elements. It has this air-cooled microturbine that creates electricity. It also creates heat. That heat can be used for cooling when we can run it through an absorption chiller. And then we can store that heat. We also have the possibility of connecting our cars or batteries to this little microgrid, which will make up for for the renewable energy feed-in, which can be unreliable at some times. And so when you put all this together, we can see some benefits. Another one, we've been doing some work in this urban farming. So here we have urban agriculture, aquaponics, and so on. Well, now we have our stormwater management low-impact development. So we have stormwater treated through LID. We have more concentrated wastewater. And by the way, one more thing. The purple is natural gas. The yellow or orange is heat and energy. The blue is water. The black is fertilizer. And the green is CO2. So we're starting to see these loops, trying to close these loops. But anyway, so here we have on-site energy and nutrient recovery. So we get natural gas from the anaerobic digestion. And then we have our air-cooled microturbines. And so now we're going to have is combined carbon capture, cooling, heating, and power. So we take the CO2 from that and inject it into our urban farm. So CO2 levels are higher. We also need to heat these in the wintertime. We can heat our local compost and make it have more natural gas. And we get natural gas from our landfill. So thinking about trying to close some of these loops and thinking about how we might connect some of these things. Another thing is what we call transit-oriented development. It's the creation of compact, walkable, mixed-use communities centered on high-quality transit systems. Here you can see the transit system. But it's a walkable community with mixed land use, reasonable density, and multiple modes of transport: walking, rail, car, bike, and so on. Another thing that people have been talking about, and we've heard in the news, a number of large companies going to invest in autonomous vehicles. And I got some interesting numbers here. So if we have 80% penetration of autonomous vehicles, only about 28% of the cars that we have on the road will be there. So it'll be a tremendous reduction in the number of cars running around. So maybe we don't need to add more lanes. We have a 72% reduction in parking space, or that turns out to be a 24.7% reduction in the impervious area for stormwater runoff. And then that means at the end of the day, we can get 17% of the city land for green space and stormwater management. So that would be a big advantage. So now, what can we do when we put all these things together? The list is here. Low impact development, gray water reclamation, rainwater harvesting, air-cooled microturbines, residential PV, thermal storage and energy storage, vehicle to grid, urban farms, transit-oriented development, autonomous vehicles. Well, we put those together and we have decentralized water infrastructure, energy infrastructure, increased neighborhood amenities, mixed land use, and preferred neighborhoods, and greater adoption. And then the possible accumulative synergistic effects are shown here. Reduce water and energy consumption, lower dependence on centralized systems, larger share of renewables, reduce vehicle miles traveled, better air quality because of that, increased tax revenue, and enhanced resilience. So we still haven't done the work yet to look at how these all things, when we put these things together, what the possible benefits are, but that work is coming. So the next thing I want to talk about, I've talked a lot now about systems, But what is this management of complexity? What is complexity all about? First, I want to show you what, on my idea, what the development train is. First, you start over here. This is what complexity is, managing the complexity. That is getting the right amenities together so we get higher adoption of more sustainable infrastructure. Then the next step is to predict the demand for urban infrastructure. Then we identify opportunities for different options for that infrastructure. I showed you some just a moment ago. And then evaluate the sustainability and resilience performance, all on the computer. And then the last step is to build that infrastructure. We certainly wouldn't build 10, 30, 50 billion dollars of the infrastructure without first checking out how effective it might be. So those are the 5 steps that we have to follow. And we've gotten up to this step here for one technology. But in order to do what I showed here, we have to build all of these models together to predict how well it performs together. Okay. So complexity results from the interaction of diverse entities, not just faces, but it's peoples, firms, infrastructure, and so on. And properties emerge from this. So let me show you an example. It's a little clearer. So down here we have, on the micro scale, we have homes where we live, where we work, where we shop, and how businesses operate. And in this social economic environment and infrastructure systems environment, those interactions cause emergent properties like, this is the land use plan for Atlanta, the quality of life, and then last, the footprint for water, carbon, and so on. So unlike what we've done in the past for engineering, like we designed this building, what we want to do is design the whole city infrastructure that creates the quality of life that we want. I think it would be a bad idea, don't you think, if we designed a transportation system that created bad air quality and congestion? Why didn't we think about that from the beginning instead of afterwards, where we're trying to fix the problem? So that's what it's all about, managing complexity. So what we do is we put together amenities that people like, and we get a greater adoption of more sustainable infrastructure. That's how it works. And here's some examples. We've been talking about this. Quality of life, gross domestic product, water and energy consumption, land use, accessibility, congestion, and so on. I wish I had time. I don't really have time to talk about those emergent properties, but here's an emergent property, ozone. This is for Atlanta. When it turns red, we're in the zone where we're not in attainment, according to the EPA. And by the way, that area right there is all those black lines are freeways, and this is one that goes around the city. Okay, so how do we go about managing this complexity? Well, one way is to collect data out there. It could be both structured news reports, product reviews, or unstructured, such as social media. Here's some pictures. And what we do is we analyze that information to think about the topics. What are people talking about? And then we develop these models that represent their decisions and how they interact with one another, and then what properties might emerge as a result of that. So that's the way we go about doing this. And I wanted to show you an example where we actually have done this. And I need to, I'm going to show you a case for decentralized energy production where we've gone through all 4 of those first steps. Okay, so first thing we did, I need to tell you, is that I have information on 1.3 million parcels in Atlanta. You give me the climate file, I can calculate the water and energy demand for approximately 1 million buildings. And so just so you know what it looks like, 'cause it's kind of pixelated here. When you put the pixels together, you can't really see anything, it's a glom. But if you zoom in, you can see what we really know. All of these parcels, road type, zoning, assessed value, tax value, year built, number of stories, etc. And then we can use agent-based models to predict future scenarios. This is business as usual, and you can see that there's a lot more yellow, which is the low to medium density residential areas, and it's really grown out tremendously versus the 2005 case. And over here we have more sustainable development. We really haven't grown the yellow at all, we've increased the density. So that's what we really want to do, is continue to keep that density. Because if you have more spread out people, they've got to get to work, they've got to get to places they want to go, so that means you need more cars, more air quality issues, more congestion, etc. So then what happens if we use this combined heat and power that I mentioned, this blue sky it? All the new development, we put in this air-cooled microturbines. And we get a 69% reduction in the energy from the grid. And over here, the evaporation, we reduce the amount of water that we need by 60%. What a huge improvement. So we started with social decision-making, managing the complexity, predicted demand for urban infrastructure. Then we looked at one option for satisfying that demand, that decentralized combined heat and power. And then evaluated the sustainability and performance metrics. Well, here's the water use, but we also have CO2 emissions. CO2 emissions dropped by 23%, or 0.007 gigatons of carbon. Multiply that by a couple hundred cities, you're starting to make a dent in the gigaton problem. The NOx values dropped by 65%, which has a huge impact on local air quality. And actually, it turns out to be cheaper. Well, according to our estimates. But I always like to use the pi rule. You know what the pi rule is? You take your cost estimate and multiply by pi. Or 3.1416. Just joking a little. Okay, so that's about managing complexity. How about future cities? What might they look like? And I'm really kind of running out of time here, so I shouldn't spend too much time on this. But this was predictions that came from a panel headed by Dr. Morgan, the Director of Engineering and Education at the Royal Academy of Engineering, looking with award-winning architects and lecturers. But anyway, and the ideas they came up with is, and 3D printed houses already exist, but building your own microclimates. I don't know about bridges that span entire cities. Sounds like a lot of material. But anyway, underwater cities, floating cities, because now the sea level rise, who knows? Super deep basements and so on. They had a few pictures. So here's a picture of the super deep basement below the Houses of Parliament in England. And then here's a floating city, for whatever that's worth. And then high-rise farm, I don't know. Have the cows up on top of the roofs, maybe. Well, anyway, what we hope is, as we move forward, is we want to develop this meta model that begins to link all of these infrastructures together in their performance. You know, transportation, buildings, water supply, energy, and so on, and try to visualize what various options might look like. And then from that, figure out which option is the best. So again, our idea is, first of all, we look at a city. It's an ecosystem of things. And resources flow in to create that ecosystem, and waste flow out. And what we want to do is maximize the creation of comfort and wealth, the creation of infrastructure that creates comfort and wealth. That's our main objective. So 3 steps in that, or 5 as I showed before. But first one is social decision making. Second one is predicting the demand for urban infrastructure. Third, looking at options for satisfying that demand. And then predicting the performance. If the performance looks good, let's think about building something along the lines of what we've come up with. Okay, summary. Well, here's some of the emerging engineering solutions. You know, sensors, social media, to understand stakeholder preference. The idea I've already mentioned, managing complexity, to create these more sustainable and resilient systems. Transit-oriented design, bike-friendly neighborhoods, shared autonomous vehicles, and we've talked about decentralized water and energy production, batteries and solar-powered transit and other things. And over here, energy-independent buildings, high-performance buildings, and so on. So, putting these together. So, final thoughts. So admittedly, the challenges that we have are, and the magnitude of what we have to do is frightening. just going to point out that even at 2 degrees, even at less than 2 degrees, Arctic sea ice disappears. Droughts spread through the subtropics and are accompanied with heat waves and intense fires. For the unacceptable future, 5 to 6 degrees, they would be warmer or hotter than it have been for 50 million years. The Arctic would be ice-free all year round. Most of the tropics, subtropics, and mid-latitudes would be too hot to be habitable, so we're going to have our own little geo-engineered microclimates. And sea level rise would be large, fast enough to coastal cities around the world would be largely abandoned. So sometimes you might ask, well, when I heard your talk, are you a pessimist or are you an optimist? And I'm putting myself in the middle. I'm a pragmatic possibilist. And I gave you some ideas for that. Okay, so last slide here. All urban systems are connected and more efficiency can be achieved by looking at their interactions. Looks like decentralized energy and combined heat and power could save energy and water. Decentralized water and low impact development can save water, energy, and money. And of course, land use is vital. And maybe these agent-based models that we use to try and predict the adoption of more sustainable infrastructure are good ways to look at the way that we can look at the adoption of various policy instruments. And with that, I'll close and take on any questions that you might have.
Oh, thank you for the talk. I've heard about this trend that people in the geek sphere that people try to live off the grid, but it takes a lot of area. Like you have to have a huge garden to raise all your food stock. So with this trend to live off grid, or like New York to be centralized, people say that New York's actually the greenest city in the US because it's the most centralized one. So every kind of resource is used to its maximums. How to solve this apparent paradox to live off grid so that actually the city spans further, or to live centralized like New York?
Yeah, well, I think it really depends on the situation. It has to be evaluated one at a time. But I think you're talking about off the grid to the extent that you were just describing wasn't really what I was thinking of. We could still have our same city makeup, but now instead of having a centralized grid that's far, far away, where we basically use a fuel, coal for example, to create heat, which then is used to power a turbine that then creates electricity. So by the time that electricity comes to the plug here, you've only got around 32% of the energy that you put into the system appearing at the plug. And then most of the energy went up into the atmosphere, and we had to use water to, to reject heat. And so a lot of that energy just evaporates water. So what I was talking about was decentralized combined heat and power, where now we have a furnace that's located near the place, a furnace that creates electricity near the place that we have an office. And we use that heat for heating and cooling. And so that's what I was talking about. And then for the decentralized water problem that I was mentioning, is that right now that storm water is a problem, but in fact it's an opportunity. If the water coming out of the sky is probably the cleanest water we have. So if we could capture that and use that for rainwater harvesting, and then recycle within buildings and communities the gray water, so we could use that for outdoor irrigation and the like. I think that's what I'm talking about by decentralized systems, as opposed to I've got my 10 acres and I'm going to grow everything I can, and I'm going to have net zero water and net zero energy. Well, we multiply that size of the land by the number of people we have on the planet. No, it's not going to work. So even in New York, there's opportunity for these decentralized systems in terms of the LID, low impact development, as well as the rainwater harvesting. And even at Battery Park, right in Manhattan, there's the, I forgot the name of the building, where they have gray water recycling, where they use that water they clean it up and then use it for other purposes. So there's still opportunities for saving more energy and water. And you have a great point there in terms of Manhattan and New York City in particular. Most of the amenities that people need every day are right there. And the concentration of people is really high. So they can afford to have high quality transit. But that was more of an accident than design. That transit system was designed in 1850. So it turned out to be a good idea. So anyway, I don't know if I answered your question, but.
Can I have another question? Imaginary scenario, by replacing all the cars in this world to, like, say, Tesla or power owned by biofuels, which one is actually a greener approach, electric car or biofuel car? Speaking of water consumption and things like that.
Well, you can take a look at, for biofuels, how much water is required. It's a huge number. And it drives me crazy. Sometimes you see the cars, like the Prius, it says 0 emissions, or the Leaf, the Nissan Leaf. 0 emissions. It's like, are you kidding me? Where do you think it gets its energy? Not to mention the fact that 25 milligrams per mile wear on the tires is coming off and containing some really nasty chemicals besides. So it's not 0 emissions by any means. But so you have to really do an evaluation to see which would be better. For the case of the Tesla or electric vehicle, if it's supplied by renewables, then that makes sense. Here you can see the numbers for water use. You can see how much, well, we got to do it compared to the benchmark. So the benchmark is unleaded gasoline, 0.32, right? Yeah. So if you have corn ethanol, it's 4.35. That's a lot more water. But more importantly, with a life cycle assessment, what you'll find with corn ethanol is you put 1 unit of energy in, and you get about 1 unit of energy out. So it's not making a whole lot of sense. All you've done is made in our country, the farmers in Iowa rich by demanding more for the corn, and so with the limited supply of corn, the value of corn goes up, and so the price of corn goes up. Not to mention it interferes with the price of food. Well, here you can see switchgrass irrigation. If you irrigate switchgrass for biofuels, it could be a really large number. So the question is, how much water do you have? So in the end, what we're going to have to do is really think about the source of how much water do you have? Does it make sense? Et cetera, et cetera. So, for example, here's concentrated solar power, where we have, mirrors in a tower, and then the sunlight shines up on there, and you get molten salt. And you use that molten salt to heat up water to drive a turbine. You can see that the numbers, it's not too much different than unleaded. Well, maybe double, but in any case, maybe that's an option. Anyway.
Thank you.
Any other questions?
Covered a lot of subjects, I know. Yeah.
Very interesting talk. So in one slide, you said so energy for water and water for energy. So in your opinion, so is energy more of a problem or water is more of a problem?
Well, the answer is on a slide. I know I showed you a lot of slides, but you can see the answer here. The answer is energy is more of a problem. But might as well look at the numbers. Where are you? Right there. So here you can see this is evaporation. So the number for water demand in Atlanta is about 107 million gallons per day. The amount of water required for the energy production is 921. It's a big number. So if we implement combined heat and power where we're using air-cooled microturbines, we reduce, this doesn't change much. The domestic water demand doesn't change much, but we get a huge reduction in the amount of water that we need. It drops from 921 to 364. The difference between those two numbers is of 3 times the domestic water demand. So thinking about breaking the energy-water nexus is very important, and water is more important than the domestic consumption piece.
Another question.
Yeah, we can hear. Yeah.
I can hear you.
Okay. So for a gig city like Hong Kong, so we have many existing centralized facilities. We have many drinking water treatment plants. We have many wastewater treatment plants. So even for water, so we have a water supply department, and we have a drainage service department. So two departments are responsible for drinking water, wastewater, respectively.
Yeah.
So not to mention, so you have transportation, you have city development, you have many other departments. So to combine, to consider everything together, more economically, ecologically. So who is going to coordinate this? Who is going to manage this? So
Well, I guess the city government will have to manage it.
okay.
And that's a short answer. But I think, you know, there's a lot of things that Hong Kong has done right because of the fact that they don't have much water. You know, they use seawater for the toilet flushing. I don't know how many of you know that, but you probably never tasted the water in the toilet, but it's salt water.
Okay, another question. Oh, one more. So in one slide, you showed on the roof of a building, there are some course. There are some course.
Yeah, but
so how
that's,
to-
I don't know if that's, it was just well, I might as well go.
So if you have those you have those animals on the top of the roof.
That was an idea. I should
How to
have. I should have deleted this slide. But this came out of this study by, Dr. Morgan, who's the director of engineering education at the Royal Academy. So
because
some
you
idea.
have those animals on the top of a roof, so that may cause noise, may cause unpleasant odors,
Yeah.
and many other related issues.
Yeah, could be.
Maybe I just make a comment along the line about the second questions from Sunlu. Now, I'm working in the government for the urban planning and also the advisory board on the environment. And actually, your talk is good in a way that if someone gives you a land without people, without infrastructure, then you can put all the best technology on this land and then use your model to optimize the best way so that to reduce any environmental impact, to have the best energy generation. But then in reality, when we really work on the land, just like yesterday, we have the meeting with the government, talk about the new development of a new town in Dongchong in Hong Kong. And then wherever the city we want to deal with, there's a people there. And different group of people have the different interests. So the town we want to develop related to the dolphin. And then no matter how you develop your town, once you hit right the survival rate of the dolphin, white dolphin in Hong Kong is the most important thing. And then there's no way to let you use. And then we talk about renewable energy. And then the two electric power company have no problem, technology problem, no problem to develop the renewable energy. But the thing is that once they generate the renewable energy like an offshore wind farm, this is low carbon emission compared with the coal burning. No problem to come up with this renewable energy. But the basic question is that once we use these new technologies to generate renewable energy, then the Hong Kong citizens have to pay additional electricity costs. Then it is another issue. No matter how keen is this technology, once you hit the daily life, the living standard of Hong Kong people, they have to pay more. Again, there's no way. No matter how good is the idea it is, even how it can reduce the greenhouse gas emission, it can reduce the environmental impact, but there's some other issue.
So how much value do you put in a cyclone?
So the point
No,
is
I mean, seriously.
Yes.
What if you had more cyclones coming into town?
Yes.
Would that matter?
Is matter?
Because of the fact that now all of a sudden, see, that's the whole problem is that
Right.
you haven't calculated the cost
You're
of
right.
you haven't really truly covered the cost of what we call the externalities.
Yes, yes,
Like, for example, your energy supply system, if it creates PM 2.5 and people die prematurely,
Yes.
what does that cost? Well, that's not part of the calculation.
It's not in the calculation. It's
Right.
very difficult
But
to
if it's,
calculate.
yeah, so, but
Right.
I don't know. I mean,
No, I
what
want
are
to say
the-
is that it is good for this kind of idea, but then in reality, it is a lot more complex
yeah.
than
Oh,
just a model.
I didn't say it was
Yes.
easy. And in fact, the one thing I didn't emphasize enough was the fact that we look at social media to try to understand exactly what you're talking about.
Yes.
And I don't talk to a group of 100 people in a room. I talk to 2 million people because I analyze what they're thinking.
Yeah.
So I have a better idea what 2 million people. You can have these limited stakeholder meetings and you got 500 people show up. That's not 2 million. By using social media and big data analytics, I can really figure out what people are thinking. And the things that we still don't know for sure is, but it looks like if we add more amenities together, then the adoption rate will increase. So, I mean, if now all of a sudden maybe you don't need a car, or maybe all of a sudden, the air quality improves dramatically, or now you have more green space. People like that. So when you start putting those things together, maybe you could increase the adoption rate and also increase people's acceptance. So I'll give you one more example when I talk about this models, agent-based models. So what we can do is what we've done is we use Amazon's Mechanical Turk. I don't know if you've ever heard of that, but basically it's a survey instrument where I can survey Atlanta and have the same demographics as Atlanta. And then I ask them questions, and then I take those questions and I build a model that reflects their wants and desires. And then with that model, I challenge it with different policies and try to predict what the adoption rate is. And I go back to that cohort of individuals I developed and tell them that this is a policy that we want to implement. What do you think? And it could be really negative or it could be really positive. But at the end of the day, I can see whether the model works by comparing what the model predicts and what people actually would decide. And I say, hey, okay, that's 2 steps. The third step is to develop educational material so people really understand what the impacts of the choices that they make are. And so we provide those resources to our cohort to see if that changes their opinion and their behavior. So that's like what we call citizen capacity building. Because at the end of the day, maybe Hong Kong is a little bit like the US. It's the citizens and what they want really matter a lot. So, and I think that's the biggest challenge. I think that's the biggest challenge, is to think about the fact that, we want to have buy-in from the stakeholders to adopt more sustainable infrastructure. All you need is like 15 cyclones coming to Hong Kong every year. Maybe that would change their opinion a little bit about climate change. I don't know. So I mean, the problem with climate change is we're all in it together. So we all have to be working on the problem.
I think the understanding of climate change, yes, it is needed, but then whether or not the people want to pay additional cost, right? They in order to change this scenario.
But I showed you for the decentralized energy production, it was less money. I showed it was less money. I gave a joke about pi rule, but it looks like it could be less money. Because as you point out, there's only one thing more powerful than Mother Nature. You know what that is? Father Profit.
Yes.
Right? So if it makes sense monetarily, then it makes sense.
Yeah. But
And I gotta say something about this. When you talk about, do you know that fossil fuels have a subsidy of $500 billion a year? Did you know that? 500 billion. So when we hear people complaining about 30 or 40 billion for subsidizing fossil fuels, renewable energy. Now I understand that we need to have the subsidies because every country like China or America, they have their own, they want to have their own energy supply. So they want them, I get that. We need to have subsidies so they generate this economy around the energy so that they all, from sovereignty point of view, I've got my energy supply, China's got their energy supply, but at the end of the day, the subsidies for fossil fuels is enormous compared to renewables. And there's a cost learning curve. You know what that is? You know, for renewables, it's something like this. For every 100% increase of implementation, the price drops 20%. It's not going to go to zero, but you know, it's going down, 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 down. Pretty soon it's going to be grid parity, pretty close. So.
The subsidy for the fossil fuel, how that is calculated?
Well, it's either by tax breaks or direct money.
Oh, it's not that low undervalue of the natural resource.
No. It's hard cash, either by tax breaks or real money. So it's a lot of money.
Yeah, lots of money.
Yes. Well, I know these days the super majors, oil companies are having trouble, but.
Yeah, I have basically more or less same question on this sustainability. It's a good idea, it's a good intention, but just want to hear more of your discussion on this human factor. It's really complicated. Because you see, on one hand, we see the global warming, this greenhouse gas emission, and all of a sudden, you know, everyone wants to drive SUV now. It appears people are not that reasonable or rational. And you look at Australia, people are willing to suffer shortage of water. They accept desalinated water, but reject recycled water. And you know, in nowadays, a few people can change the whole thing and really make things better or worse. And, it's just hear more of your discussion on this human factor and related to this sustainability and the long-term thing.
Well, I think citizen capacity building, make people understand. There's a limit to what the Earth can supply. And I know you have a small country that's on your border called Bhutan. Ever heard of that country? Of course you have. And they have a metric that might be interesting to think about. We all think about gross domestic product. They have one called gross domestic happiness. I don't know if you ever saw that. So the idea is this. So, there's this thing called affluenza. Affluenza is this disease that's caused basically by, you want more and more and more, and you're never quite satisfied. And the idea is that this is the amount of resources you need to be happy, truly happy. But then you want a little bit more and a little bit more and a little bit more and a little bit more. But at the end of the day, you're never any happier. So you got to be able. At some point, we got to start thinking about managing expectations. So I'll give you an example, a personal example. When my daughter was in the 4th grade, she had me come over and give a talk about global warming. So I gave a talk about global warming, and all the kids were so excited about hearing what the problems might be in the future, and they were all just like, we got to do something about this. So I came home the next day, and my daughter says, well, what are you doing about that, Dad? So at a very young age, the young people understand. And so it's not about more and more and more. That's not necessarily a road to more happiness. And you get at a point that I think it's hard to describe. What I can tell you, though, if we're going to double the urban infrastructure in the next 25 years, we can't do it the way we have. The world's environment, the climate, the renewable resources, the flow of material through our society, it's going to be, it won't be sustainable. So
So it's also probably religion is part of the picture also.
I guess so. Value systems, whatever they
Yeah.
start with, religion of various sorts.
Yeah. I have a question. Last question.
Thank you for your talk. It was very interesting. So about a few months ago, there was also a speaker from the States, from the Rocky Mountain Institute, who gave a very similar talk, where he talked about, his focus was on energy, and he said a lot of the same things that you said about decentralization and becoming more sustainable and things like that. So my main understanding from his talk was that in terms of technology, with retrofitting of buildings to make them more energy efficient, with decentralized sources and things like that, and just a smarter way of operating the grid. In terms of technology, it is actually quite doable within the next 20 years or so, 20 to 30 years, that the US can become fully off fossil fuels. That was my impression that I got in terms of technology. But the bottleneck is more of the economics and the politics and just changing the way things are being done. So, so could you comment on that, please?
Yeah, well, I think, I'm not sure it can be done just in 20 years, but I mean, I have to really look at it in detail. I'm trying to remember the name of the CEO of the Rocky Mountain Institute. Anyway, but I think that we just have to begin the discussion about alternatives for energy and really factor in the cost, the true cost, what we call externalities. What is the cost of excess asthmas or premature death resulting from the use of fossil fuels? What is the true cost of the changing climate, the rising seas, and so on? Those numbers are huge. So I think it makes sense to think about alternative energy supplies, and not just. There's also another one. There's megawatt, and then there's also what we call negawatt. Negawatt as a negative, meaning that rather than trying to build more and more energy to feed the beast, think of ways of conserving energy, using energy more efficiently and more wisely. And I think that's one of the messages from the Rocky Mountain Institute as well. So I don't know if I answered your question. You can elaborate.
Well, I guess what I was looking for is some confirmation or maybe some disagreement as to whether that view is overly optimistic or is it justified?
Well, I think it's justified. I mean, think of it this way. We use about 15 terawatts of energy in the world. The sun shines down on the earth is 186,000 terawatts of energy. So there's surely some ways to a future that doesn't use renewable energy. There's no doubt about it. The problem is that we have the super majors and the coal companies that have these assets. One in our part of the world is the tar sands in Alberta. That balance sheet is $10 trillion. Someone owns that balance sheet. Are they going to leave that stranded in the ground? If you were the person that owned that, so when you go to the bank and you want to borrow money to do something in the future, you say, hey, I've got $10 trillion worth of tar sands in the ground that I can borrow against. Are you going to give that up? No, you won't. But if you make a carbon tax such that it has to be a stranded asset, then we've got, then we got something. And one more thing is that if you look at Wall Street, for example, they're asking questions about that, about a company's future, their future liabilities if all of a sudden we do have a carbon tax. Because now all of a sudden, hey, I have to leave that $10 trillion in the ground. I can't, that's a stranded asset. I can't use it. And I was at ExxonMobil about 6 weeks ago, and we had a chance to talk to the younger engineers who just joined ExxonMobil. And then we asked the question, okay, so what is it about ExxonMobil that you would like to see in the future? And they said, well, you know what? ExxonMobil is an energy company, but we would like them to be an energetic company. And I thought, what does that mean? Well, what it means is that ExxonMobil are experts in offshore, you mentioned wind, in the construction of offshore technology. They're experts. They do it all the time. They make this platform where waves 50 feet high go by. They could easily talk about applying that technology to, harvesting wave energy, flood energy, wind energy. They could do that easily, but they're not.
Good. With that, let's thank Professor Crittenden again.